All right, dear students, here I'm providing you one more video tutorial about the hybrid materials. And the learning objectives for this section of hybrid materials are basically the following three levels. So first, we would like you to understand the potential of hybrid materials. So as you can see in the course of this lecture, we're basically adding more and more complexities to what you learn. So if you remember from the very beginning of our course, we started with, let's say, simple material or pure material in a very simple shape, either round or rectangular, something like that. And we started even with the more or less one simple material property, let's say maybe several qualitative properties, but one quantitative property. And then we add a little bit complexity for you to think about, let's say, optimization of certain objectives. We consider mass and stiffness and mass and strength at the same time. So we learned about material index and so on. And the more, so you have learned, let's say, shapes. So you know, in reality, you cannot just use a uniform shape or just a panel alone, or basically a bar alone. So we always try to manipulate the shape for our design. This week, so we are adding also a little bit more flexibility or complexity about the materials. So that is basically the hybrid material. And the skills and abilities basically are, after this course, you're able to use the synthesizer to explore material combinations. So if you have practiced this a little bit during the week with the EduPack already, that's excellent. So if you're still waiting or hesitating on how to get it started, at the end of this lecture, I will just show you a little bit about it, maybe a part of it only. And of course, you can visit the exercise session to learn much more about how to use this synthesizer for your tasks or for your future applications. And the last is to give you the inspiration, basically to learn. And there's a way or there's something new to think about when you want to get better properties, basically to combine, let's say, materials to create hybrid materials. And there will be also another way to design new materials, which will be given at the end of the course as well. So the resources are the chapters we have already defined. Another resource I would like to mention is the website that defined by given by EduPack. Actually, there's a quite good reading material about the hybrid synthesizer tool, and you're very much recommended to read it if you're interested in it. All right, the outline of today's lecture, this video tutorial, basically are the four elements here. So first, I would like to show you what hybrid materials are, and why do we need it, and what can they do, and what should be our action plan or strategies to design these hybrid materials. And followed by that, I try to give you one example of hybrid materials, which is this sandwich structures. Actually, this is a type of structures you really often see in our daily life. And a third part is going to be a kind of a part of the synthesizer I was mentioning, so which is called part cost estimator. As we know, the hybrid materials are good, but what about the cost? Right? So this is a way for you to really put things in practice when you try to kind of realize your hybrid materials. And the last point is about next generation material design. So we know from this course, you have a kind of tool and capability to design your hybrid materials. But if we want to go deeper, if we want to get some fundamental or revolutionary materials, out of our study, what can we do? So the last slide, I'm going to show you what is about the next generation material design. All right, so first I'd like to give you some, let's say, daily life practice about hybrid materials. So this is a basically boat, if you still remember from maybe the first or second course that given by Professor Sven Bossip. So we started with this. Remember, we learned basically how to define material index and how to make maybe penalty functions as well from this structure. What I would like to show you here is, if you just look at a little bit in detail, this boat actually is consisting of lots of hybrid materials. So the most obvious thing about this sails, so this is just not some simple, let's say, texture or wood. It is already hybrid materials, and the same goes to the mast and also the hull. So the hull is a typical sandwich hybrid materials, and it's basically consisting of carbon fiber and PMMA foam core. We have learned, many of the material index, and basically for us to use those hybrid materials in those advanced structures like boat is to maximize the material index, or the material indices. And we want to have an excellent material property, basically. But as you know, from our many discussions in the courses, the material index cannot be just a single. So we talk about, let's say, the stiffness or specific stiffness, because we always want to minimize the mass, or strength or specific strength, and so on. But we don't only talk about, let's say, tension. We don't really only talk about stiffness. We need to consider both, or even more, so I'm not listing more. But we need to also consider, let's say, more loading cases in reality. In your exercises, we simplified a little bit, but in reality, not all the structures are always under one loading type, right? So basically, we need to consider a system of material index, and to maximize or to optimize all of them, it's not easy, and there's often not one material type that could fulfill such a goal. And even more advanced, or even further, is we also need to consider, let's say, other properties like thermal properties, like optical properties, and more. So in the past, we always put them as a constraint. Basically, you only have, let's say, a qualitative measure or qualitative requirement about that. But most often, you also want to have a certain, let's say, quantitative requirement about your thermal conductivity, electrical conductivity, and so on. So you need to train them even as an objective, than just a constraint. So dealing with all these optimizations of material index, can we have better materials, basically? If we just take a deeper look, so this is a simple modulus density diagram. So we have density as the x-axis, and the Young's modulus as the y-axis. So our materials, nature materials, engineering materials, so they are really lining up always in this proportional direction, something like this. And we want to naturally, for many structural applications, actually we want to get something like what? We want to get something here, right? In this area, which is a hole. Basically, we have no materials available. If we just put some, let's say, contours there, which is this E over rho, and we want to maximize this for many of the cases. But at a certain stage, like here, basically you have nothing to choose because we're running out of our engineering materials. But there's still quite space empty here. Yeah, can we get better materials? Yeah, which are exactly fulfilling this whole. Well, this direction we used to as our material index to choose or select the engineering materials now is the vector for material development. Basically, we want to get new materials in this direction, fulfilling this whole area. And same applies to the strength density diagram. So this is the same diagram, basically the same diagram we have C. So here we have the strength, yeah. And the whole is even a little bit more dramatic. So it's always a little bit different when you just deal with let's say different properties. And if we just also plot the contours of sigma y over rho, you see we're running out of our engineering materials, existing engineering materials, even faster. So there's a huge area, a big hole remaining here that we have no materials possible. Yeah, so basically here is our limit. Of course, if you combine stiffness, strength, and more, you will see we have really a bigger hole to kind of fulfill. Yeah, and of course, yeah, this is the vector of material development for the strength and density. Yeah, and the reality could be even more complicated. I mean, because we don't always deal with the mechanical properties, as I mentioned. So here I'm showing you thermal conductivity versus Gauss modulus. Yeah, so you can see we have metals which are naturally having really high strength and also high thermal conductivity. And we have our, let's say, elastomers, polymers, which are softer and also have basically no thermal conductivity. So here we are having a huge hole existing. Yeah. So in many cases, we look for, let's say, stiffer and thermal conductive materials, but in other cases, we also want to get some materials right here. So we want to get something less stiffer, more soft, yeah, but still thermal conductive, right? Like in your task, maybe you see there's some soft material that could be easily moving your finger with to get some touch-free activities, right? So there's a big hole for us to fulfill. Yeah. So what could be the solution? So here I'm showing you one possibility to do it. We know copper is a very good material for thermal conductivity, and rubber is completely the opposite. And what if we just combine these two materials into one? Yeah. So don't think about the processing at this moment. Just think about if you can combine them. Yeah. So here I'm giving you one basically idea. So we have rubber as our matrix, and we're just putting some copper wires into our matrix in a way, inside or outside. And if you just gave 30% of your copper wire into your rubber matrix, you can see you would reach a material already less stiff, yeah, but still quite thermal conductive. And if you just decrease the volume fraction of copper to 10% to 5%, you will see we basically created some new materials or hybrid materials which are fulfilling this hole. Yeah. So this is something we want. We want to get a big space of possibilities of materials that we can easily choose, no matter which directions we're going. Yeah. And this is basically simple example to show you the power of hybrid materials. And here I'm giving you a little bit more proper strategies for how do we design hybrid materials. And in principle, there are actually two strategies overall. And the first one is more, let's say, material science and engineering related. Basically, you are doing hybrid things, or you're designing your materials at a microstructure level or even finer level. So here you're still creating something, let's say, globally, if you just look at from meter scale, from centimeter scale, it looks like one material. But if you just zoom in, you're actually designing more new materials. Yeah, you could control basically the microstructure of it, and you could control the alloying design of it. Yeah, then you could use, let's say, different phases, different grains, different inclusions or precipitates, all these features to design something completely new in terms of mechanical properties. But globally, yeah, it looks still like one material. Yeah. So this is the one path about designing, let's say, hybrid materials or new materials. And the second one is more mechanics driven. So this is actually the concept we're going to focus on our course. Basically, we accept properties as given. Yeah, so we use existing materials. We're not trying to design materials from, let's say, atom level, from microstructure level, basically everything below micrometer level. We're designing things in a little bit upper scale, yeah, at millimeter level or centimeter level, or even bigger, let's say. Yeah, and we just play with the geometry. So the geometry, you'll be seeing them in detail in the next line. So we take existing materials and we try to design new materials via so-called geometry. And the third solution is something a little bit more specific. We're not going to touch it. I just tell you what is it. It's about tactile technology. This is very much related to fibers. Yeah. So you want to use certain fibers to improve the material properties. Yeah. And in our course for the hybrid materials, we will be very much focusing on the second one, which is the mechanics kind of driven concept. And we want to use the freedom in terms of geometry to design our hybrid materials. So to be more in detail, I gave you basically 4 classes of the action plans for the designing of hybrid materials or manipulating geometries. So the first is about cellular structures, second is composites, third is sandwich structures, and the fourth is multi-layers. Yeah. So just to give you the design variables for all these different, let's say, structures or action plans, what we could have basically is choice of materials. So in most cases, you are dealing with more than 2 materials in all the structures. So which types of materials you would like to choose? You want to choose copper fiber, or you want to choose aluminum and polymer, something like this. And volume fractions. So how much should I put, yeah, for your 2 or even more materials into these new materials? Configuration. So configuration means how you're going to design it in a cellular, in a composite, and in a sandwich. This is a little bit more, let's say, given, but for the other 2, it could be a design parameter. And the connectivity. So you're going to connect your design elements, or you're going to put that into a separate case. And also scale. Yeah, scale means you're going to use thin and, let's say, or thick, the cellular structures or things like this. To give you more, let's say, details, you can see some specific design variables into the corresponding structures. So this is about the composites. Yeah, as you can see, we have basically 3 kind of configurations here. Yeah, the first, let's say, is unidirectional. So you have just your fibers or wires in your matrix, and it's aligning one direction. Yeah, of course you can imagine this will make your material highly anisotropic. So when you just pull it vertically, it will be very different from you pull it horizontally, just due to the configuration. And already something more exciting is about so-called quasi-isotropic. So you have, let's say, 3 directions. Basically, in this case, when you pull it vertically and horizontally, your material will behave similar. Yeah, but if you pull it with a different, let's say, angle, rather than horizontal or vertical, the material will behave already, again, anisotropic. But this is another kind of configuration. And of course, you can also use particles, which is a little bit more homogeneous, but it will also be completely different behavior when you just use wires. So these are all the possible, let's say, design variables or concepts you can think about of composites. And for cellular structures, we also have foams, honeycombs, and also triangulated lattices. They're just listed here. So this is basically foams. You have learned this from the book. And a honeycomb is something very, very popular too, especially in all the different energy absorption systems. And this is the so-called lattice materials. If you have learned something about, let's say, additive manufacturing, which is very good to produce lattice materials. So here, as you can see, this is a typical BCC structure. And we also have different kind of types of lattice structures to play with. So for each of them, you can think about, we can play with the volume fraction, the scale, so how thin it would be, how thick it would be, and all the design variables you could control. And we also have the sandwich structure. So there are two different kind of sandwich structures you can see here. And this is the symmetric sandwich structure. Of course, it can be, asymmetric. So basically, we will have not, let's say, two equal-sized layers, top and bottom, but different thickness or different volume fraction, and also could be different areas in case of certain applications. Well, so this would be some basic, let's say, architectures about hybrid materials. And there could be many more. Here, I'm going to give you one example about sandwich panel, design of sandwich panel to fulfill, let's say, certain design properties. And we have now the core material, which is B, and we want to have some face materials as A. You have a given dimension already. So if we want to just get multiple, let's say, properties improved, what can we do? And we first think about elastic response. This is about stiffness. You can think about panel stiffness simply. But as I said, we do not want to consider only stiffness. We want to also consider strength. We want to consider a failure property. So as you can see, if you just deform more and more, you could have your face material yield, which is plastic deformation. That is already one type of failure in many cases. And even more severely, you could have some buckling. You could have the failure of your core. So these are all the design, let's say, material properties we could think of, right? And most importantly, we want to add something about thermal and electric properties into the plane. That is our original, basically, motivation to use the hybrid materials, right? So all of this could add their weights into your design of your hybrid materials. So in this specific case, actually, I'm just showing you for us to improve, let's say, the flexural modulus and versus density. So if we just consider aluminum, as our let's say the material A, so the face material, and the so-called polymer foams as the matrix, as the core materials. So as you can see, the pure of both of them are basically quite far away. And if we just look at the criterion of excellence, basically. So here we're talking about the bending stiffness. You see, they're both not optimal. And now by just playing with this simple criteria, which is the thickness of the material A, so thickness of your aluminum alloys. This is also a way of playing with this volume fraction of material A, of course. And you can see, we actually created a series of new materials. Yeah. This is, let's say, 10mm PVC inside and 3mm aluminum alloy 6000 series T4. Yeah, if you know how it's produced, it's called T4. As the face materials, we're creating something here, which is already better. Yeah, if you just look at the slope here, than aluminum itself. Yeah, that's quite interesting. And if you go further and further, as you can see, we're just really going to very optimizing direction. If I just now make a, let's say, a maximum that we have designed, basically this is it. This is the material you could really have a optimized stiffness plus your density altogether, which is a hybrid materials that has something like so this is a little bit disturbing. Yeah, something like 0.1mm aluminum alloy, as the outer layer, and 10mm PVC as the core material. Yeah. All right. I think now you can feel the power of hybrid materials. Yeah. So here I'm just telling you one thing. Yeah. So which is this the optimization of the bending stiffness. But this gives completely different functionality of your materials, as you could imagine, because the aluminum itself is good, providing sufficient bending stiffness. But the thing is, aluminum is highly thermoelectrical conductive. If you're in application, you're looking for some thermal or electric resistance, and this material will be a perfect choice for you. And because it is providing very good specific bending stiffness, and it is also thermal resistance, which is much more better than the other polymers and the polymer that we have initially right here. Yeah. All right. Of course, I have showed you all the good things about hybrid materials. But you know, there's no free lunch. Yeah, nothing is perfect. And as you could imagine, hybrid things are good. But as you can just use this kind of analogy here, we produce the hybrid corn. You know, they're very good. So we have very much improved the yield and also hardness. And but it is very infertile. Yeah. And the same applies to our engineering materials. When we have hybrid cars, you know, they're low fuel consumption, very good at the environment, very low emissions, and so on. But they're expensive, right? So that's why I'm here introducing you something more specific, which is this kind of synthesizer model for the part cost estimation. So this is a very interesting module that you have provided. Basically, you've learned how to use it and before about the cost factor, not this specific module, but you learned about the cost estimation in the past. And but that was something just to play with our value, right? And here it is giving us a much more systematic and complete cost model. So if you just look at the constitutions here, so if we go with the material A and the material B, let's say imagine you got all of them out. So imagine your material A is just, let's say, a pure aluminum alloy or pure, let's say, carbon steel that we have. And the material B is, let's say, is a hybrid material that we would like to have. And you want to compare the cost. It's not easy to compare because the material production is a long chain of different processes. That's why in this kind of cost estimator tool, it is basically giving the cost estimation through the whole process. So it includes, let's say, the raw material, and the forming processes and surface treatment and assembly method. So it gives you really an overall cost model about producing the materials. Yeah, so as you can see here, this is to produce a total part of this door panel. Yeah, so this is existing for any kind of cars. So usually these are made by some carbon steel or simple steels. And now we want to have a hybrid material, which is a combination of steel with 20% of PP. So in this panel, obviously you could see this is lighter, and this is lighter than steel, and it could save 15% of the weight in this case. Yeah, so the question here is what about cost? Actually, as you can see, yeah, as I mentioned, so I'm sorry it was not listed here. The black, the material A, material 1 is the simple steel. Material B is the hybrid material, this 20% PP kind of hybrid material. And the solution is perfect. So this 15% saving of weight actually also has a even lower cost. Yeah, and you might ask then why we're not using on time. And so here I'm giving you a little bit more detailed explanation. So here, as you can see, this blue is corresponding to material A, material 1. And this is just simple steel or pure steel. Yeah, and this yellow is material 2, which is this 22% of PP. And as you can see here, yeah, the material cost, indeed, the hybrid material is cheaper. Yeah, but what we need to think about is also the batch size. Yeah, because the material cost does not, let's say, stay constant when you